Section 4.6, Variation of Parameters. In the last couple of sections, we've been looking at the method of undetermined coefficients to solve problems of the form ay double prime plus by prime plus cy equals f of t. It turns out that the method of undetermined coefficients is not always applicable to these problems based on the form of the forcing function f of t. We said before that the method of undetermined coefficients works when f is a polynomial or an exponential or a sinusoid or some kind of sum or difference or product of those types of functions. But there are many functions which don't fall into that category. For example, f of t equals the square root of t, or ln of t, or tangent t, or a rational function of t, or an absolute value of t. There are many functions for which the method of undetermined coefficients simply does not work. So what are we going to do to solve these non-homogeneous problems? Well, first, to develop that, we need some background. If we look at ay double prime plus by prime plus cy equals f of t, and we call that non-homogeneous equation, we call it equation n. Remember, we've always looked at the associated homogeneous problem, ay double prime plus by prime plus cy equals 0. We'll call that h for homogeneous. And we know how to find the general solution of this based on the characteristic equation. So let's act like we found the general solution, y sub h, and it is c1y1 plus c2y2. We know that the form that these functions y1 and y2 take depend on the roots of the characteristic equation. They depend on whether you're in case 1, case 2, or case 3 of our analysis before. So whatever those are, let's call those functions y1 and y2 of t, they're called a fundamental solution set or a fundamental set of solutions for the associated homogeneous problem H. In terms of in linear algebra lingo, they form a basis for the solution space of the homogeneous problem. Okay, so what does this have to do with finding a particular solution of the non-homogeneous problem for a general f of t, if f doesn't have the type of form that we've seen in the last couple of sections? Well, it turns out the people that came before us said, why don't we look for a solution, yp, that has the form v1 of t times y1 of t plus v2 of t times y2 of t, where v1 and v2 functions are yet to be determined, and y1 and y2 is the fundamental solution set associated with the homogeneous problem. So remember, y1 and y2 are known, v1 and v2 are yet to be determined. So let's call this equation 1. It's our form of our y sub p of t. And our goal is to find functions v1 and v2 that will make this be a solution to the non-homogeneous problem. Now, keeping with our themes from before, if the form 1 is indeed a solution of the non-homogeneous problem, we know that we can substitute it back into equation n and get a logically true statement. So what happens? We know to plug this back in, we need to get our hands on yp prime and yp double prime. So looking at this, let's go ahead and calculate yp prime and yp double prime. So yp has this form. Notice since everything here depends on t, just for sake of convenience, we will suppress the t notation, but these are all functions of t. So if we take the derivative of yp with respect to t, using the product rule, we get derivative of the first times the second plus the first times the derivative of the second. That's the derivative of this term. Applying the product rule to this term, again, derivative of the first times the second plus the first times the derivative of the second. Now, we know that we need to take another derivative, and this is already pretty complicated. It involves 4 products. So if we just straight away took the second derivative now off of this line, we would have 4 product rules to do. So we're going to make a move, and we're going to see if we can get away with it. So here I've underlined the terms that involve derivatives of v. So this is includes a v1 prime, this includes a v2 prime. Notice this term has primes involving y1, and this term has a prime involving y2, but y1 and y2 are known functions. So if we know y1, we're going to know y1 prime. If we know y2, we're going to know y2 prime. So these primes don't cause us as much computational difficulty as having these primes. So here's the assumption we're going to make, and we're going to see if we can get away with it. Let's assume that the v1 prime y1 plus v2 prime y2 combination combines to give us a 0. We're just going to see if we can find a solution. Remember, we're just looking for any v1 and v2 that will make this a solution. So we can impose any assumption that we want to, and if we get away with it, fine, because we don't have to find all solutions. We're just trying to find any one solution. So we're going to impose this extra algebraic constraint that v1 prime y1 plus v2 prime y2 is equal to 0. Let's call this equation star. And the reason that star is nice is it's going to reduce our workload here, because if these two underlined terms combine to give me a 0, then now the only terms that are remaining are these two in yp prime. And that's simpler, and it only has half as many product rules in it. All right, so if this is our yp prime under this assumption, then we'll calculate yp double prime. Again, it's two applications of the product rule. The product rule here gives us this. The product rule here gives us this. And now we have our hands on yp double prime, yp prime, and yp. Let's substitute them all back into the differential equation and see what happens. So if we do that, we get a yp double prime plus b yp prime plus c yp has to equal f because it's supposed to be a solution. And now when we substitute y in here, y prime in here, and y double prime in here, then we're just going to algebraically simplify. And if we expand all this out, and then we collect the terms in a very specific way, and I've tried to help us keep track of what's going on by color coding these. So just imagine that we've multiplied this all out, and then what we want to do is we want to gather the terms, all the terms that have a v1 in them, and I've underlined them in green. And then we want to gather all the terms together that have just a v2 in them. I've underlined those in blue. And then everything else either involves a v1 prime or a v2 prime. So think of these as the prime terms. They're highlighted in red. So if you gather things together according to this color coding scheme, gather all the things that have a v1 prime or a v2 prime in them, they have a common factor of a. We'll gather them together and factor out the common factor of a. If we gather together the v1 terms, it has a common factor of v1. We'll factor that out, and this is what remains. And then if we gather together the v2 terms, they have a common factor of v2, and this is what remains. So notice this is just an algebraic rearrangement of this. Now, stop for a minute and look at what's happening with the green and the blue. Remember, y1 and y2 are not random functions, but they are a fundamental solution set to the homogeneous problem. That means they themselves individually are solutions to the homogeneous problem. That means when you plug them back into our differential equation, ay double prime plus by prime plus cy, it has to give us a 0 because y1 is a solution to the homogeneous problem. And the same thing goes for when we plug y2 in. So that greatly helps us because it says that this highlighted term in green becomes a 0 and this highlighted term in blue becomes a 0. So at the end of the day, we just have this term has to equal f of t, and we'll call that equation double star. Now, this, if you notice that our unknowns here are v1 and v2, so we already had one equation in v1 and v2, although it's in v1 prime and v2 prime. So let's gather our first equation that we called star here. Let's gather our second equation that we called double star here. And let's look at them together as a system. If you put them together, we end up getting two equations in two algebraic equations in the two unknowns, v1 prime and v2 prime. It's very important that you realize this isn't a system of differential equations from our perspective, but rather a 2x2 system of algebra equations where the unknowns are v1 prime and v2 prime. Okay, so if you rewrite those, and here all I did is I took and I divided both sides by a. This is our double star equation. This is just a rewriting of our single star equation. Hopefully that helps you see that this is a system of two algebraic equations in the two unknowns, v1 prime and v2 prime. So after a little algebra, you can find what v1 prime and v2 prime are. It takes a little bit of work, but when the algebraic dust settles, this is what you get for v1 prime, and this is what you get for v2 prime. You can check me on that. Now, if you stare at this closely, there's a familiar quantity in the denominator here, and this is just the way that the algebra shakes out when you solve this for v1 prime and v2 prime. In the denominator here, you get a y1, y2 prime minus a y1 prime, y2. That is something that we've encountered before. That's called the Wronskian of y1 and y2. And that same term, or that same quantity, occurs in the denominator of v2 prime also. So we can rewrite this in a way that's a lot more convenient to remember, that the numerator is minus f times y2. So for v1 prime, the numerator is minus f times y2, and the denominator is our constant a, our leading coefficient in our equation a, times the Wronskian of y1 and y2. Similarly, v2 prime simplifies to our forcing function f times y1 all over a times the Wronskian. Now we're not done, because we were looking for the functions v1 and v2, and we don't have those functions yet, but we do have their derivatives. And once we have their derivatives, all we have to do is integrate both sides of this equation, and we'll have our hands on v1, integrate both sides of this equation, and we'll have our hands on v2. So here I've just written that down. If we anti-differentiate, we get our hands on v1, anti-differentiate, we get v2, and now we'll box these in. This is the recipe for the v1 function and v2 function that we needed to make our form. Remember, we had this form. y1 and y2 were a fundamental set of solutions for the homogeneous problem, so they're known. And now we have formulas for finding v1 and v2. And notice what those formulas consist of. They involve our forcing function. The v1 formula involves the forcing function, and it has a minus on it. It involves the second member of our fundamental solution set, and in the denominator it's a times the Wronskian. This v2 function involves our forcing function without the minus. It involves the first member of our fundamental solution set, and its denominator is the same. Okay, so our conclusion is that our yp, we were looking for a particular solution of the non-homogeneous problem, and it ends up being v1 y1 plus v2 y2, where here's how you find v1, v2, and we already know how to find y1 and y2. Okay, let's look at an example. Let's find a particular solution to the differential equation y double prime minus 2y prime plus y equals e to the t over t. Notice undetermined coefficients doesn't work here, because this is a quotient of two functions that we know how to handle. It would be okay if it was a sum of these two functions or a product of these two functions, but when it's a quotient of these two functions, undetermined coefficients doesn't work. And we'll take t to be positive, so we make sure that the denominator is not 0. So the method of variation of parameters, and I should have said this earlier, where the name comes from, is if you think back when we were solving the homogeneous problem, we're very used to doing this for the homogeneous problem. So some books call this method variation of parameters, some books call this method variation of constants, and the idea is we're used to doing this c1y1 plus c2y2 when we're building the general solution to the homogeneous problem. And then this form that we looked for was a variation of that theme, because we are varying the constants and making them be functions instead. So that's where the name comes from. Okay, so back to our example. So we want to use this method called variation of parameters. The variation of parameters techniques just says you're going to look for a yp that looks like v1 y1 plus v2 y2, where v1 and v2 have the integral formulas that we had boxed in above. So in order to prepare ourselves, we know that we need to get our hands on the y1 and the y2, so we'll take the associated homogeneous equation. We'll write down the characteristic equation, we'll find the roots, we'll see that we're in case 2, we'll write down our YH, and so we will just take this to be our Y1 and this to take our Y2. It doesn't matter if you were to switch the order of these, you just need to be consistent all the way through. Whatever you take as your Y1 and whatever you take as your Y2, you just can't switch them as you proceed through the problem. So I'll take my Y1 to just be this. I don't need the C, I just need the function. I'll take my Y2 to be this. I'll go ahead, I know that I need to calculate the Wronskian of my Y1 and Y2, so I'll go ahead and do that. The Wronskian is just the determinant of y1, y2, y1 prime, y2 prime. Notice there's a little product rule here to compute the derivative. And then we'll take the determinant of this 2 by 2 matrix, upper left times lower right minus upper right times lower left, you get this. And then when all of the algebra is finished, the Wronskian ends up being e to the 2t, which is never 0, but we knew that because if these are a fundamental set of solutions, then they have to be linearly independent, so the Wronskian can never be 0. But the bottom line is the Wronskian of the y1, y2 is the quantity e to the 2t. So now we're ready to go. We know our yp is v1y1 plus v2y2. We'll write down the formula for v1, and these are just formulas that you have to know. It's the integral of negative f of t times y2 of t all over my leading coefficient a times the Wronskian. So if you look above, this is my f of t in the original problem. Here's my f of t. My a is 1. We already calculated the Wronskian just a moment ago. We have the Wronskian. So let's put all of those pieces in place. We have v1 is the integral of minus f times y2 all over a times the Wronskian. So it's minus my f times my y2 all over my a times my Wronskian. So notice there's a lot of cancellation that happens here. The t's cancel. This e to the t, this e to the t multiply and then cancel here. And we end up with a very nice just integral of minus 1 dt that is negative t. We don't need to add the plus c here because we're not trying to find every possible v1. We're just trying to find some v1 that works. So we found v1. Let's proceed and find v2. So v2, following the formula, is the integral of f of t times y1 of t over a times the Wronskian. Here's my f of t, here's my y1, my a was 1, and here's my Wronskian. Notice again, these multiply and then cancel here. We just get the integral of 1 over t dt. That is ln of absolute value of t. But if you remember in the problem, they told us that t was positive, so the absolute value of t is the same as t. So we just get ln of t as our v2 function. Now we just need to assemble the pieces. Our yp, the particular solution that we're looking for, is v1y1 plus v2y2. And this is guaranteed to be a particular solution of our non-homogeneous problem. Notice this is a completely different method than undetermined coefficients. It starts differently. The workflow is very different. It is much more widely applicable than the method of undetermined coefficients. But if we're being honest, practically speaking, in practical problems, these integrals can be very difficult to do. So this is why we don't only teach the method of variation of parameters, is because if we relied on it for everything, these integrals can become unwieldy. Sometimes they work out nicely, and this example just shows that this was a problem that we could not have solved by undetermined coefficients, and yet we were able to do it with the method of variation of parameters. Okay, let's look at another example. Let's find a particular solution of the non-homogeneous equation y double prime plus y equals tangent t. Now this is a function that is not in the wheelhouse of undetermined coefficients, so we have to recognize that and pivot to variation of parameters. Once again, we're going to get our homogeneous equation, find the roots, and get our solution. This is going to be my y1, this is going to be my y2. I'll go ahead and calculate the Wronskian of my y1, y2, of my y1, y2. So this is the determinant of y1, y2, y1 prime, y2 prime. We calculate this determinant, and after a little bit of algebra here, we see that the Wronskian is 1. So this is a very nice Wronskian. Variation of parameters says that our template for yp is going to be v1y1 plus v2y2, where my v1 has this formula. So let's just put in the pieces. This is an integral of minus my f times my y2 all over a times my Wronskian. So if you look at this integral, it's a negative tangent t times a sine t, but we could turn tan t into sine t over cosine t. Then we get a sine squared t over cosine t. And we can rewrite sine squared t as 1 minus cosine squared t. Then we can separate this into a 1 over cosine t minus a cosine squared t over cosine t. That gives us a secant t minus cosine t. Remember the minus I factored out from all along from the original formula. And now we'll just distribute this minus. I get negative the integral of secant t plus the integral of cosine t. And this integral is straightforward to do. This integral you might have to remember from Calculus 2 that the antiderivative of secant t is ln of absolute value secant t plus tan t. So we'll put that here. Somewhat complicated, but that is what v1 is. Now let's find our v2. So the formula we have here, I'll just do integrate my f times my y1 over my a times my Wronskian. This one is a little more straightforward. Again, we get a tan t times a cosine t this time. If we rewrite tan t as sine t over cosine t, the cosines cancel. It's a very straightforward integral. So our yp would look like, I don't rewrite it here, I guess I do rewrite it down here. Our yp looks like v1 y1 plus v2 y2. So here's my v1, here's my y1 plus my y1, my v2 times my y2. So this would be your particular solution to the non-homogeneous problem. Okay, so the idea here is that variation of parameters always works in theory. So there was nothing in the theory here that stopped us from using this method. Practically speaking, the difficulty of the integrals involved normally limits the applicability of variation of parameters in practice. We've already seen a couple of examples to where it works out very nicely. If you were to just say, well, I'll never do undetermined coefficients, I'll always use variation of parameters, you should try that a little bit, and you'll quickly see that while it may be theoretically doable, the integrals can become much more work than the method of variation of the method of undetermined coefficients was itself. So I think that the way to think about it is when you have certain functions like polynomials, exponentials, sinusoids, sums, products, or differences, undetermined coefficients is going to be a more efficient method to use. The integrals that are involved when you have those functions can become very difficult. On the other hand, you might encounter problems like the examples that we saw here that don't fall into those categories of functions, and your hand is forced. You just have to use a different method, and the method of variation of parameters comes to the rescue. So try that in the homework and see how it works for you.